To solve the Riemann hypothesis, the Hilbert-Pólya program asks us to build a specific mathematical machine, an operator, whose energy levels match the zeta zeros. The WEIL explicit formula provides the rigorous test for this machine. It evaluates any candidate operator, confirming whether its internal structure matches the specific distributional signature of the zeta zeros. This diagram shows the requirement for a passing grade. The machine must output an atomic measure, meaning its data takes the form of perfectly thin vertical spikes separated by empty space. Approximations do not work here. Any valid operator must inherently produce these razor-sharp discrete points to pass the WEIL criterion. When attempting to build this machine, mathematicians often reach for the most convenient tools available, Fourier multipliers and spatial translations. These tools are popular because they commute. Their order of operations does not change the result, keeping the underlying calculations stable and clean. The challenge is structural. We have to determine if a machine made exclusively from these cooperative, smooth-running parts can capture the jagged, discrete coordinates of the zeta zeros. While mathematical convenience offers an obvious shortcut, this very simplicity might actually disqualify the tool from the start. A same-space Fourier multiplier works by collapsing multiple actions, like the smoothing of data, correcting the phase, and shifting into one environment. Because these factors commute, the entire assembly diagonalizes. It condenses into one single straightforward multiplication operation. Every mathematical operation produces a footprint, known as its gram form. This animation shows the footprint of that Fourier multiplier. It always produces an absolutely continuous measure, a smooth, unbroken wave of data that flows across the axis. The architecture of a Fourier multiplier ensures its output is always smeared. It is structurally incapable of isolating a single point. This diagram places the requirement directly next to our tool's output. On one side, razor-sharp atomic spikes. On the other, a flowing, continuous wave. A smooth wave cannot mathematically equal a discrete spike. We can attempt a workaround by narrowing the continuous wave, squeezing it horizontally so tightly that it begins to mimic a discrete point. Calculus demands a penalty for this, known as a concentration cost. As we tighten the focus around a single point, the local mass, the density of the function, is forced to inflate. If you push that resolution toward an infinitely thin pinpoint, the required energy simply blows up to infinity. The formula does not fail gracefully. The attempt is mathematically rejected. No amount of calibration can make a continuous tool produce a discrete reality. The shape of the math itself forbids it. A same-space multiplication operator either produces empty space or infinitely thick plateaus. It never outputs the exact, discrete eigenvalues required for the Hilbert-Pólya spectrum. This does not disprove the Riemann hypothesis, nor does it end the Hilbert-Pólya program. What this proof provides is a permanent stop sign for the specific shortcut of using commuting smoothers in a single space. Viable models now exist in more difficult territory, shifting the focus toward non-commutative spaces, changing finite intervals, and complex boundary conditions. By permanently closing the easiest door, this proof stops researchers from wasting time. It forces the field to resolve the singular concentration and non-commutative geometry required to solve the Riemann hypothesis.